Let's apply the same principles of a vertical parabola with a horizontal one instead. Notice the similarity between the forms of the equations with our vertical and horizontal parabolas. Instead of y equals ax squared plus bx plus c, we've transposed the x and y values, making y our independent variable and x as our dependent. And here, compare it to y, or f of x, of a x minus h squared plus k. Also notice how h and k have switched places because we've transposed x and y. A lot of the same features still apply. So when we look at our vertex form, we see that our parabola still has a vertex at h and k. We are just looking at the different part of the equation to identify h and k. And instead of an axis being a vertical line, it's now a horizontal line at y equals k instead of x equals h. Instead of opening up and down, our parabola opens right or left, again based on whether a is positive or negative, and then the amount of dilation remains the same, based on the a value. So when graphing parabolas, whether it's horizontal or vertical, if we're given a parabola in standard form, we can go ahead and start with the vertex. If it's not in standard form, we need to go ahead and use completing the square to get the parabola into standard form. So here we have our parabola in our standard, the vertex form. So when we compare it to our formula of a y minus k squared plus h, we see we have an a value of 1, a k value of negative 1, and we have an h value of negative 4. Since our vertex is h and k, our vertex is negative 4, negative 1. Because it's a horizontal parabola and our a value is positive, we know it's going to open to the right. And since it opens to the right, our axis is going to be a horizontal line at y equals, passing through the vertex at negative 1. So when we start with our vertex and our axis of symmetry, we know that our graph is going to open this way. Well, what we can do now is actually use an XY chart to figure out some of the points and get a more precise graph. The difference here is when we do an XY chart, traditionally we're picking values for x and then plugging them into our equation to solve for y. However, given that our parabola is opening to the right, if I pick some value of x, I'm going to end up with 2 points, 2 different values of y when I solve, because we don't have a function, and x is not our independent variable, y is. So instead, what we're going to do is we're going to pick values of y and use them to solve for x. So instead of picking a value of x near the vertex, I'm going to pick a value of y, like 0. If y is 0, we can evaluate for x. So looking at our original equation, we can solve for x when y equals 0 by substituting in 0 with y, and then solving. We get 1 squared minus 4, which equals negative 3. So we get the point negative 3, 0. We can plot that point. And then additionally, because we have the axis of symmetry, since this point is 1 unit away above the axis, we know that there's going to be a symmetrical point 1 unit below the axis as well. So using the axis, whenever we find one point, we found another as well. So now we can go ahead and find a second point. Well, we just kind of can keep going up. Since I already did x, y is 0, now what if y was 1? We can solve. 1 plus 1 squared minus 4. 2 squared minus 4 equals 0. So we have the point 0, 1. Since this is 2 units above our axis, we'll have a symmetrical point 2 units below the axis. And 5 points is enough for our parabola. So we can smoothly connect the lines, and we have our parabola graphed. Now that it's graphed, it's much easier to see the domain, as well as the range. Domain, we notice, actually starts at our vertex at negative 4, and continues forever in the positive direction. While unlike with our vertical parabolas, the range is actually going to be the continuous one, negative infinity to infinity. This graph is forever going down as well as forever going up. And so you'll notice how domain and range has kind of switched their relationship With the vertical parabola, domain is all real numbers, and the range is based on the vertex. That relationship switches when we change to a y-squared parabola instead. Here, this parabola is in general form, so we need to rewrite it into the standard vertex form. So just to make it a little easier, we'll go ahead and set the right side of the equation equal to 0. We'll move our constant term. And since we do have a leading coefficient that's not 1, we'll go ahead and factor out the negative 1. Giving us y squared minus 2y equals negative 5 plus negative 1 times whatever in the box. So our b value is negative 2 divided by 2 squared gives us 1. So we factor, we get y minus 1 squared equals negative 6. We move the negative 6 back over by adding it. And then that's our equation. X equals negative 1, y minus 1 squared plus 6. We see we have a value of negative 1. We have a k value of 1. And we have an h value of 6. So our vertex is at 6, 1. Go ahead and plot that point. Since it's a horizontal parabola, we know our axis of symmetry will pass through the vertex at y equals 1. And since our a value is negative, it's going to open to the left. Let's go ahead and use an XY chart to fill in some points now. Now y is our independent variable, so let's pick some values of y. Our vertex is at 1, so let's say 0. 0 is pretty easy. We'll plug in 0 into our equation. So we want to solve. If x equals negative 1, we have 0 minus 1 squared plus 6. So we're going to get negative 1 plus 6, which equals 5. So we have the point 5, 0. And then using the symmetry of the axis of symmetry, we get another point of 5, 2. And then let's go ahead and do a y value of, let's say, 3. 3. So x equals negative 1, 3 minus 1 squared plus 6. You get negative 4 plus 6 equals 2. So we have the point 2, 3. And then using symmetry, we get the point 2, negative 1. And then all we have to do is smoothly connect our dots. And we have our parabola. Looking at the domain, since it opens to the left, that means it's negative infinity until the vertex. The vertex is an ending point for the domain. And our range is, of course, going to be negative infinity to infinity.